to his wife, Marjorie, who was here in attendance, for establishing this really key namesake lecture in his name and that honors his legacy at The Ohio State. And clearly, his legacy has always extended far, far beyond The Ohio State University. Now, it is my privilege to introduce Professor Scott Levi, PhD, who is Professor and Chair of The Ohio State University Department of History, who has the esteemed honor of introducing tonight's speaker, Dr. Levi. Thank you.
Welcome, friends, and thank you very much, Dean Bradford. Good afternoon. On behalf of the Department of History, it is my pleasure to introduce you to our 17th John C. Burnham Lecture in the History of Medicine and Science. To test or not to test, tools, rules, and corporate data in U.S. chemicals regulation by the Thomas M. Siebel Professor of History and Science at Princeton University, Angela N.H. Creager. It's correct, we did not have a Burnham Lecture last year, we missed one. And so this year, the lecture is going to be twice as good. Professor Creager studies the history of 20th century biomedical research. She graduated from Rice University with a double major in biochemistry and English. I like the humanities angle there. And completed a PhD in biochemistry at the University of California, Berkeley, where she developed an interest in the history of biology. Supported by postdoctoral awards, she retrained as a historian of science at Harvard University and MIT, and joined the Princeton History Department in 1994. Her first book, The Life of a Virus, Tobacco, Mosaic Virus as an Experimental Model, 1930 to 1965, came out in 2002. That book shows how a virus that attacks tobacco plants came to play a central role in the development of virology and molecular biology. I'm sorry, I'm a Central Asianist. Those words don't flow off my tongue. It takes a little bit of practice. Her second book, Life Atomic, A History of Radioisotopes in Science and Medicine, came out in 2013. And that book traces how and why artificial radioisotopes were taken up by biologists and physicians and examines the consequences for knowledge and radiation exposure. She's also the co-editor of 3 volumes, most recently, Science Without Laws, Model Systems, Cases, Exemplary Narratives, came out in 2007. She currently directs the Shelby Cullom Davis Center on the theme Law and Legalities. Please join me in welcoming Professor Angela Creager.
Great, thank you. It's a great pleasure to be here today. And I should say, actually, I'm no longer now directing the Shelby Cullom Davis Center, but I have moved over to being chair of the history department. So I have even more in common with Scott Levi than you might understand. The first order of business, okay, is of course to thank the Ohio State University Department of History and Health Sciences Library, Medical Heritage Center, as well as Marjorie Burnham for bringing me here today to give this lecture. It is such a pleasure to give a lecture in person, even if much of the audience is remote. Giving Zoom talks where you feel like you're talking into outer space is really a discouraging and strange experience. So my special gratitude to all of you for being here and for enabling me to come in person. And special thanks to Carol Bradford and Scott Levi, as well as Rhonda Maynard for making this possible today. I do think I had the chance to meet John Burnham. I don't remember whether it was a History of Science Society meeting or a meeting of the American Association for the History of Medicine, both of which he was actively involved in, but I definitely remember his voracious curiosity and his support for other scholars, especially emerging scholars. So it's a real privilege to be able to give a lecture named after him. And today I'll talk about my latest project, which is actually on the realm of science and law, looking at regulation and the way in which new knowledge and new technologies coming out of biomedicine inform regulation and where they don't and why that is. Now, let me see if I can turn this on. Okay. Nope. How do I turn it on, Rhonda? Sorry, I'm new to the setup. Is it that button? Ah, got it. Excellent. So the government regulation that I'll be discussing was prompted by the need to protect people from new cancer-causing chemicals and pollutants, consumer products, foods, and drugs. But how does one determine which chemicals are the dangerous ones? Human experiments with potential carcinogens would, of course, be unethical, and epidemiological studies are lengthy and stringent and often miss low-dose effects. So toxicologists have conventionally relied on testing substances in laboratory animals to assess hazards to human health. The standardized tests that they have developed occupy a central place in generating the evidence for regulatory decision-making. Now, toxicology is not the only sphere in which standardized testing plays a central role in decision-making. Whether it is nuclear weapons, education, automobile safety, or medical diagnosis, in the modern world, testing has become a critical form of assessment and governance. And I'll just mention that Trevor Pinch's classic article on the sociology of testing is a touchstone for my consideration of tests for carcinogens. Now, out of a tradition of using animals for testing, after World War II, toxicologists developed a standardized test for carcinogenicity using two species of rodents, rats and mice, and long-term exposures at half the maximally tolerated dose. Animals surviving the 2-year course would be sacrificed and examined for the appearance of tumors, of course, alongside any animals that didn't make it to 2 years. These were costly experiments, and their results were not beyond question due to differences between species, the toxicity of many substances tested, their relatively high dose, and the inherent predilection for tumors in the rodents. Yet there were really not good alternatives for assessing the health effects of long-term low-dose exposure. And thousands of new chemicals were entering workplaces, foods, drugs, consumer products, and the natural environment, particularly with the petrochemical revolution of the 1950s and beyond, using oil as a feedstock to make synthetic chemicals. And just as a loop back to my prior work, I might mention that studies of ionizing radiation, which were really often done under the context of atomic energy organizations, national agencies, really propelled the understanding of low dose and long-term exposures. At this point, ionizing radiation is essentially the best studied carcinogen because of concerns that applications of atomic energy, both military and civilian, might affect the human populations they were supposed to be benefiting. So in the 1970s, scientists introduced a new generation of short-term tests for carcinogenicity, for the ability to cause cancer, using microbes and cultured cells instead of animals, and to look at the effects of exposure to chemicals. These assays drew on new ideas about the role of DNA mutations in causing cancer, as well as in advances in bacterial genetics, cell culture technologies, and molecular biology. So my current book project looks at the trajectory of one of these tests. In the early 1970s, biochemist Bruce Ames developed a simple Petri dish assay for mutagenicity based on strains of a well-studied bacterium. And I'll describe that test in a moment. But to give you a sense of the overview, in the early 1970s, this new tool, usually called the Ames test, offered a quicker and less expensive way than traditional rodent testing to identify potential human carcinogens among the tens of thousands of synthetic chemicals on the market. And there was an opportunity to implement broad testing due to the sweeping environmental legislation of that era. However, in passing a comprehensive Chemical Safety Act, the Toxic Substances Control Act of 1976, in the end, the US government did not require mutagenicity testing of chemicals. So why not? That's in many ways what this lecture and essay aimed to answer. The scholars critical of the current state of chemicals regulation almost inevitably point to the lack of data, of toxicity data, as a problem in trying to improve the control of chemicals. So my lecture sketches out why the lack of testing may have arisen in response to regulation. In other words, the regulatory process itself became implicated in the lack of data, particularly for commercial chemicals. As legal scholar Mary Linden has observed about US chemicals regulation, ignorance of toxicity may be an advantage to the product. So the remainder of my lecture consists of 3 parts. First, I'll describe the scientific development of the tests in question. Then I'll look at the emergence of environmental law under Nixon, and then why this particular law failed to increase testing in the US. So I'll start though with some familiar but important background to my story. In 1962, Rachel Carson's Silent Spring focused concern on the dangers of agents such as DDT and synthetic chemicals and industrial pollution, what she called the so-called elixirs of death to humans and wildlife. Now, historians have since documented how the massive impact of this one book drew on several other developments, such as debates over radioactive fallout, the fouling of rivers and landscapes with noxious industrial waste, and the loss of native plants and animals in association with suburbanization and environmental contamination. Of particular concern in this era was the role of food additives, pesticides, and pollution in human cancer. By the late 1960s, the US federal government targeted cancer from chemicals as a key public health problem. In 1968, the National Cancer Institute launched a plan for chemical carcinogenesis and prevention of cancers. And then during the subsequent years, that agency publicized an estimate that as much as 90% of human cancer was due to environmental agents. As NIH Director Robert Stone spelled it out in 1973, most known environmental carcinogens are a result of our increased agricultural and industrial technology. And I'll just mention, and I'll touch on this at the end, that very notion that so much human cancer is caused by environmental agents became qualified over the case of the 1980s and 1990s by cancer biologists who began to conceive of the relevant environment as including the body and not just what was outside it. There's a lot of DNA damage due to metabolism and just wear and tear on the body. These concerns inspired scientists to apply new molecular understandings of health and disease to the problem of identifying environmental carcinogens. Take Berkeley biochemist Bruce Ames. As he recalls, sometime in 1964, I read the list of ingredients on a box of potato chips and began to wonder whether preservatives and other chemicals could cause genetic damage in humans. Now, he had material at hand to see if he could detect mutation-causing cancers right on a petri dish. He and another microbiologist had assembled thousands of mutants of Salmonella that were unable to make, oh, I'm sorry for this display issue. Anyway, this may be on some of the slides, that were unable to make the required amino acid histidine. And over the course of the 1960s, Ames was analyzing the mutants to determine exactly what kind of DNA alteration was responsible for each disruption to the histidine biosynthetic pathway. And in effect, what you have to the left is the biosynthetic pathway for histidine. And each one of the arrows with letters above it like his G, his E, his F, et cetera, are steps in the chemical transformation of these small molecules until you finally get to histidine. This is like the assembly line for making the final product of histidine in the cell. But if one of these enzymes has, or if one of the genes encoding an enzyme has a mutation, that enzyme may not be able to catalyze the reaction. So what you see at right is what's called a prototrophic bacterial cell. It can make histidine. But at bottom, there's a His- oxytrophic bacterial cell, which has a mutation in one of these genes for an enzyme, and that basically disrupts the biosynthesis so that you don't end up getting histidine at the end. Don't worry if you don't understand the chemistry or the genetics. You've probably only heard of Salmonella because it's pathogenic in humans, but it also, this particular strain, Salmonella typhimurium, was extremely well characterized genetically early on, along with E. coli, which you probably also heard of for both reasons. And it's because of the genetics being well understood that it was being used. And just to give you one more view about how the test works, I've showed you what the mutants are like. Basically, you take one of these specific mutant strains and you add to it rat liver extract. And what this does is to metabolize that chemical into the kinds of substances that the body is exposed to when you are exposed to a chemical. What happens when we're exposed to something toxic is that often goes to our liver, and the liver, in trying to detoxify it, turns it into a variety of other substances. And sometimes, especially if it's a substance the body has never encountered before and was not evolved to try to detoxify, it actually generates a substance that's more toxic or carcinogenic compared to the original substance. So you have to look at what the liver does to chemicals to understand what the ultimate effects are on the body. Now, the mutants that Ames was dealing with were so well characterized that he knew exactly which base of the DNA was changed to make that mutant. And if you get a mutation that breaks an enzyme, you can also get a mutation that restores function if it makes a mutation in the opposite direction. And so what these strains were doing was detecting mutations that restored function. So the cell suddenly regained the ability to make histidine because the mutagen caused a mutation that restored the gene encoding that enzyme. So if you add to the Salmonella strain and the rat liver extract a possible mutagen, and you get more cell colonies on the Petri dish than you had on the control plate without that chemical or substance being tested, that's an indication the substance causes mutation. Now, as an assay for carcinogens, the Ames test relied on two critical assumptions. The first is that all carcinogens are mutagens, or at least the vast majority of them are. So human cancer in this view was triggered by exposure to environmental mutagens, and this detected mutagens, not carcinogens, but the idea was that that's the same group of chemicals. And second, it assumed that a bacteria was a suitable model organism to detect mutagenicity as it occurred in human cells. And he justified this on the universality of DNA. As you can see, as he said, oops, it may seem absurd to extrapolate from bacteria to humans, but DNA has the same double helical structure and the same 4 nucleotides in all organisms. And it is logical to believe that mutagens for higher organisms are mutagens for bacteria also. More than half of the mutagenic agents for bacteria are carcinogenic for animals. And this is in 1970 when he was just beginning to use this test. And to the left, this is just some schematic diagrams of different kinds of DNA damage that can happen. And the point is that these can happen whether it's in a bacteria or in a human cell. And cancer biologists in the 1960s and 70s were thinking this is what triggers cancer. So within just a few years, Ames's lab had shown how their new test could detect substances that caused or might cause human cancer: cigarette smoke, a food preservative, and a flame retardant. And in the case of the flame retardant and the food additive, these were banned partly as a result of Ames test results. And this tris, this flame retardant additive, you see the Science article by Arlene Blum and Bruce Ames. This is an especially interesting case because those of you who lived through the 1970s, there was a lot of concern about children's pajamas being flammable. So the idea was you don't want children's pajamas to be flammable in case there's a house fire. You don't want the pajamas to catch fire easily. And so a whole group of chemicals was developed to try to make children's pajamas not flammable. They make the pajamas basically feel like plastic. Well, it turned out that one of the most common of these, tris, that was being added to children's pajamas was in turn a carcinogen. So the Consumer Product Safety Commission, as soon as this was discovered, said we should not be putting tris in any pajamas. Interestingly, they didn't ban it from upholstery, and to this day, it's still used in a lot of upholstery. And Arlene Blum now has a Green Science Policy Institute that fights to try to get this compound out of context in which humans are exposed to it. Anyway, so you could see the power of this in the regulatory sphere. And it's important to mention that there was a big gap in what was being tested at all. So the US government, through its national toxicology program, screened about 100 chemical compounds a year. And that was out of 63,000 chemicals being commonly used in the US. Every single one of those tests required a few years, hundreds of rodents, and hundreds of thousands of dollars. The Ames test, by contrast, was quick and cheap. His own lab tested 300 compounds in just a few years and found that the correlation between mutagens and carcinogens was very high. So because of this, the Ames test was really embraced across the board. Environmentalists were very enthusiastic about it because of the potential to identify chemicals of concern. Scientists were using it, and companies were adopting the test as well, as you can see from this Gina Colada quote. She says, "This has led to a curious situation in which industries are implicitly endorsing the tests at the same time that scientists and legislators deliberate over whether companies should be forced to use them." So kind of an ironic situation. And one of the reasons that the test was so widely adopted is that Bruce Ames himself was sending the test strains to anybody who wanted them, whether they were in a company, in a research institute, at a university, whatever. And you can see already by 1975, just a few years after he kind of standardized the test, he had sent it to over 75 companies representing pretty much all sectors of the chemical industry, food and beverages, tobacco, consumer products, pharmaceuticals, and commercial chemicals. So this was obviously a high impact test. And the question is, how was it going to affect new regulation? And so to answer that question, I want to step back, and I'm sorry for the sea of acronyms. It's an alphabet soup of acronyms for the next 15 minutes, but that's how US law is. So as you probably are aware, most of the important environmental legislation that happened in the early 1970s happened under Republican president, President Nixon. And this was because this was such a popular cause that even a Republican president had to contend with the demand for better environmental law. So first, the National Environment Policy Act of 1969, which set the framework for a lot of environmental policy, founded a Council on Environmental Quality, which was to directly advise the president on these matters. And also, as you'll see, they were a very important group in the legislation I'm going to talk about. More familiarly, the Clean Air Act of 1970 was aimed at trying to clean up smog in the air. The Environmental Protection Agency was founded that same year. And the Clean Water Act of 1972 was also passed, although in this case, there was already beginning to be some resistance to these new laws. Nixon actually vetoed this law, and it was passed by a congressional majority over his veto. Now, the Clean Water Act and the Clean Air Act set out very specific goals for these two aspects of the environment. But regulation of terrestrial chemicals that weren't in the air or the water was very highly fragmented. So exposures in the workplace had long been managed through private industry standards, and after 1971, also by the US Occupational Safety and Health Administration, or OSHA. Pesticides were regulated under the Federal Insecticides, Fungicides, and Rodenticides Act, FIFRA, which went back to 1947 and was then amended at various times. The US Department of Agriculture administered FIFRA for quite some time, but by the 1970s, it was clear that having the agency that promoted agriculture regulate pesticides created a conflict of interest. They had a very light hand in regulating. So their regulation was shifted to the EPA. Safety of food additives and preservatives, as well as drugs, was overseen by the Food and Drug Administration. And then starting in 1972, the Consumer Product Safety Commission established safety standards and when needed, issued recalls for about 15,000 consumer products. Now, these are many different laws and agency, but there are chemicals, a wide variety of chemicals that didn't fall under any of these frameworks, and they were effectively unregulated by the government. I mean, industry had standards, of its own, but in terms of federal government regulation, there was no overarching law. So early after being formed, that Council on Environmental Quality, CEQ, argued for more comprehensive oversight of chemicals, and especially through its influential report, Toxic Substances. After recounting the growing number and volume of commercial chemicals in production, the report cautions these substances enter man's environment and man himself through complex and interrelated pathways. Present in air, water, soil, consumer products, and food, they pervade our environment. They often become concentrated through the food chain, with minute quantities being magnified thousands of times as they are consumed by higher forms of life. Increasingly, all forms of life are being exposed to potentially toxic substances. And the fact that so many pollutants biomagnified and PCBs was of particular concern in this decade for that reason. And at the same time, there was growing knowledge about the dangers of low-dose exposure. This meant that there was a growing alarm that contaminants that had been thought to be safe actually both got more concentrated in bodies and might be dangerous at low doses. So this was an era in which new scientific knowledge about toxicants really drove a lot of both scientific concern and regulatory concern about chemicals. So in response to this need for better environmental protection from chemicals, the CEQ staff member, J. Clarence Davies, worked with Charles Ledow, who was a Republican lawyer who'd also worked as a chemical engineer at Dow Chemicals, to make a first stab at an overarching bill to regulate chemicals, the Toxic Substances Control Act. And I'm going to talk about it through its acronym Tosca, Tosca like the opera. So when you hear Tosca, don't think of the soprano, think of this law. So their initial draft, which was circulated to other government agencies in December 1970, outlined a federal program for the systematic regulation and collection of data for toxic substances, many of which fell outside the purview of existing legislation. So it authorized the EPA to evaluate, quote, all information developed by or otherwise provided to or made available, end quote, to the government so that the chemical substances that endangered human health or the environment could be restricted or otherwise regulated. And I just want to emphasize that the legislation was especially aimed at regulating chemicals whose effects, particularly cancer, birth defects, and heritable mutations, resulted from long-term and chronic exposure and so might be missed in acute toxicity tests, tests that look at like the inflammation of skin due to exposure. So in this initial draft, companies seeking to bring new chemicals to market could be required to first show that the substances met certain health and environmental test standards. This pre-market requirement was very unpopular with industry. Their interests were represented by the Department of Commerce. So before the Nixon administration sent the bill to Congress, they sent it to the other agencies, and the Department of Commerce stripped out that requirement for pre-manufacturing testing. But testing still remained a focus of the bill and throughout Tosca's long gestation. The law was seen by contemporaries primarily as a mechanism through which the federal government could, quote, require a manufacturer or processor to test the effect of a substance on health and the environment. So ultimately, the main mechanism of this bill was supposed to be testing. So the bill was introduced into the Senate as S1478 in June of 1971. And then in July, Senator William Sponge introduced an amendment that made testing and reporting requirements more stringent. This version authorized EPA to actually say which standardized protocols for testing effects could be used, for instance, for carcinogenesis, mutagenesis, and persistence in the environment. So in other words, it put back the pre-manufacturing testing requirement that the Department of Commerce had stripped out. In hearings on the bill, a representative of the chemical industry claimed that this would, quote, impede innovation and cost too much. Industry was able to delay a vote for most of the year, but eventually the bill passed with Sponge's amendment. But the House didn't pass the amended version, but the Nixon administration's original text. And as a result, it died in committee. And this was clearly due to the involvement of industry in determining what was actually reconciled and made it to Nixon's desk. The same thing happened in the 93rd Congress, which was also dealing, of course, with the aftermath of the Watergate scandal. In July 1975, a scandal reignited political pressure for chemicals regulation. Dozens of workers at a chemical factory in Virginia were poisoned through their exposure to ketone, which is a neurotoxic pesticide manufactured in the plant. In the wake of the public outcry over this poisoning, the 94th Congress took up Tosca again, holding hearings throughout 1975. Now in hearings on the bill, supporters pointed to these new short-term bioassays for carcinogenicity that might be used in screening substances. And you see I have a quote, on the slide from a Congressman Ottinger, who pointed to the difference in cost and time between the traditional animal tests and, for instance, the Ames test, which was the leading among these new in vitro tests. Interestingly, he said this in the context of concerns about how Tosca could lighten the load of animal testing for animal welfare reasons. And that's it's interesting how this whole debate intersected with animal rights as well. So anyway, the chemical industry or the Ford administration made clear that some version of Tosca was going to have to be passed into law. And so a group of industry players began hammering out the details with congressional staffers. And one of the corporate lawyers, James T. Riley, got involved, and he described the effects of the revision as lobbying so effective in retrospect that Tosca has been less effective than the sponsors hoped. And James O'Reilly's description of Tosca, which he published in an article called Torture by Tosca, is a really great, it provides really important information from the chemical industry side on what this period was like and what the chemical industry was aiming to obtain. He left, he worked, I think, for the administration, and I don't remember if it was Carter or Reagan, but then left under Reagan. But he's a professor of law, or maybe right now retired, but still teaches some law at University of Cincinnati. He's a really interesting figure. On my last trip to Ohio, I was coming to interview him. Anyway, the key concessions into industry, many of them revolved around testing, whether it would be required, who would conduct it, and whether test results would have to be disclosed. The final bill passed Congress on September 28th, 1976, and it was signed into law by President Ford on October 11th. Now, in general, the final statute created many procedural hurdles for EPA in fulfilling its mandate to regulate chemicals. And of course, these hurdles, they weren't oversights, but provisions that were set in place due to the concessions with industry to limit EPA action. And specifically, it was the Manufacturing Chemists Association that largely represented industry here, and that's whom James O'Reilly was working for. O'Reilly, who of course was helping to write these provisions, said the bill contains such obscure and inconsistent phrases that its supporters were doomed to frustration. Even its provisions ensuring transparency of safety data, he said, became rigid procedural handcuffs. He, as I mentioned, referred to Tosca as torture and a failed statute. Kevin Gaynor, another legal scholar at the time who analyzed the law shortly after it passed, called it a regulatory morass. This was a statute that was really designed to make oversight difficult. Now, it took several years for the law to be fully implemented, and the extent of its ineffectiveness took time to manifest. And in part, this was because the anti-regulatory policies and judiciary appointments of Reagan really consolidated the status of Tosca as a regulatory failure. One key term of the law was unreasonable risk, which the EPA had to establish in order to act. But that phrase, unreasonable risk, wasn't defined within the bill. So instead, through administrative decisions in court cases, it came to refer to cost-benefit analysis as part of a larger turn in environmental regulation toward economic considerations. Now, in part because health and environmental benefits of non-exposure are very hard to quantify in monetary terms, it was and remains very difficult for EPA to demonstrate that the benefits of removing a risk outweigh the easier to tabulate economic costs of regulation. And this is just a general problem in environmental regulation when it's constrained to economic concerns. Now, Tosca gave the EPA regulatory authority over all chemicals, but the processes were completely different for existing chemicals that were already on the market, that's 60,000 or so at the time, and new chemicals, up to maybe 1,000 new chemicals that came into production. For existing chemicals, the EPA was responsible for regulating those that posed unreasonable risk to human health or the environment, and they could require companies to test chemicals that pose this unreasonable risk. And submit data. But in order to either require new testing or obtain existing data from the manufacturer, the EPA had to issue a rule. Now, the procedures under the Administrative Procedure Act are pretty burdensome. It's not easy for agencies to issue rules. It can often require several years, a few $100,000, and includes steps like getting public input and a lot of documentation. Consequently, there weren't that many rules issued by the EPA in order to try to extract data on existing chemicals. From 1976 through 2009, there were rules requiring testing only on about 200 chemicals on the market out of 60,000, 63,000. So yeah, this was not an especially effective way at trying to get data for chemicals on the market. So for new chemicals, by contrast, a pre-manufacturing notice was required. And if this gave the agency time to check out the new chemical and see if any regulatory action was in order. But the substances that didn't elicit some response from the EPA could go ahead and go on the market. And if they went into production, they were simply added to the roster of existing chemicals. So according to an EPA history of the bill, the chemical industry representatives expressed afterwards that they had agreed to even having a pre-manufacturer notice in exchange for reduced reporting requirements. So the critical issue from industry's point of view was exactly what was going to be required on this pre-manufacturing notice, or also called a PMN. As one industry scientist said, the notice was supposed to have adequate manufacturing use and biological information to permit hazard evaluation by the EPA. And under the Carter administration, the EPA sought to specify exactly which tests should be considered adequate. And the EPA also proposed a rule by which the agency could actually invalidate a PMN if it didn't have all the required information. Industry was not happy with this proposed implementation. And at hearings in March 1979, several executives expressed their concerns. Sorry, I didn't forward the slide. Edsel Blair of Dow Chemical Corporation testified on behalf of the Manufacturing Chemists Association and argued that the EPA's ability to invalidate a PMN because the company didn't comply with requirements or lacked certain data would threaten innovation in the chemical industry. As he said, we want the invalidation concept completely removed. He also objected to, quote, just too much data being requested on that form, and argued EPA should not be able to specify the required tests. As he said, we do not want a rigid set of preconceived stereotype testing procedures. Moreover, as Blair noted, nowhere in the Act does it state that the manufacturer will perform certain tests. And this, in the end, actually proved to be the law's Achilles heel as far as new chemicals were concerned. Unless the EPA issued a rule on the new chemical or its class of chemicals, filing this PMN just didn't require a manufacturer to conduct any new testing of health and environmental effects. Now, there was a proviso. The law stipulated that if the applicant, the company, possessed data, it had to be submitted as part of the PMN. So initially it appeared that inexpensive in vitro tests like the Ames test would be reported on all new chemicals, because after all, this was a test that companies were already adopting on their own. As the environmental law reporter observed a month after the bill was signed into law, in many cases, the manufacturer will submit the Ames assay results with the pre-market notification. And this built, of course, on what I've already said, that Gina Collada reported in Science, that the test was being used. But of course, any submitted data on that PMN could be used by the EPA to hold up manufacture or to request further testing. And the result, intended or not, was that Tosca created a powerful disincentive among companies for toxicity testing of new chemicals, even if the tests themselves were inexpensive and easy to do. As legal scholar Kevin Gaynor put it, a testing rule must be issued if a substance may present an unreasonable risk, while a substantive regulation may be issued only if there is a reasonable basis to conclude that the substance will present or presents an unreasonable risk. That may present requirement, coupled with minimal losses, in other words, to calculated benefits in a risk assessment caused by the testing rule, creates a standard so low that a positive result in a simple Ames test might trigger more costly testing. There's a lot of legalese, but the point is that the impact of this law was very much contingent on the exact wording of the statute and the way in which it was being implemented at this time. And although I don't have access to corporate archives, one gets the sense that testing actually begins to go down in response to a law that is all about testing chemicals. It's a very counterintuitive and perverse outcome. So in the end, remarkably few PMNs submitted to the EPA included this environmental or health testing data. Only 17% included any mutagenicity data, and most had no toxicity information whatsoever. And this paucity of submitted data came up in a 1983 Senate hearing regarding the law, when a senator asked a staff member of the Office of Technology Assessment if it was a question of money. He said the simplest test, which is a test for the capacity to cause mutations in bacteria, is not expensive, on the order of $1,000 to $2,000 at a commercial lab. I don't think cost is the reason. And later in the same hearing, a representative from Union Carbide Corporation said companies are doing more testing and they are watching the research projects more carefully with respect to the toxicology of things. But that assertion makes the lack of testing data in PMNs even more perplexing. And I can't tell if industry was doing testing and simply not submitting the data because it was so costly for the government to require it, or if they weren't doing the testing at all. But either way, the result was the data was just simply not coming to the EPA. And in fact, what the EPA ended up doing in response was to develop a computer-based kind of comparison program that's called structure-activity relationship, to allow them to try to guess, based on the chemical structure of a new compound, whether it would have toxic effects, rather than actually having any data. Industry's unwillingness to share information affected two critical aspects of how Tosca worked. The first necessary step of implementing the law was to compile a list of all chemicals in production, the existing chemicals list. This was called the Tosca Chemical Substance Inventory, and this is from their webpage now. This is an important legal tool, because the very first thing a company does when they want to make a chemical is find out whether that chemical is already in this list. It determines whether a chemical goes down the existing chemicals route or the new chemicals route. But it was impossible for EPA to create this Tosca inventory by Congress's deadline, both because coming up with the technical system to do this for tens of thousands of chemicals was actually a complex technological problem, but also because industry proved less willing than expected to share its data. And this was despite provisions to protect confidential business information. And I should just mention, on the technical front, Evan Hepler-Smith, who's a historian of chemistry, has a brilliant article called Molecular Bureaucracy that was published in Environmental History that looks at the kind of information technology infrastructure behind this law and how it was developed. It's turns out that regulating chemicals is very much a question of information management. Okay, but this unwillingness to share data relates to a second aspect of the law, which really didn't work very well. Tosca actually requires EPA to publish health and safety information on chemicals. However, the agency was also required to protect proprietary information. So companies routinely invoked confidentiality to prevent health and environmental data from being made public. And to protect businesses, the EPA resorted to using generic names for chemicals, but that made the associated health and safety data in the records, in the public records, of almost no use because the chemical couldn't be identified. So this is really about the politics of information, who has access to data, how is it used. So, and the lack of publicly available health and environmental data on high volume chemicals became something of a scandal in the 1990s because a staffer at the Environmental Defense Fund did a study to see exactly what percentage of the high volume chemicals that are sold had publicly available toxicity data. So these are the things that are produced in the highest tonnage worldwide. And what they found was that more than 70% of these chemicals didn't have any publicly associated, a robust set of publicly available toxicity data. And both the US government and industry were skeptical of that, and they undertook their own assessment and found that in fact 90% of the chemicals didn't have publicly available toxicity data. So there was then a voluntary government industry program to make this information available, but when the lawyer who'd spearheaded it retired from Environmental Defense Fund, the whole thing kind of came to naught. So, and this has been an issue also at the international level as well. And I have a whole other chapter of the book that I'm writing that looks at international regulation and struggles to harmonize regulation, and a lot of it boiled down to whether or not information would be shared from companies to the public, and not least between over national borders. So let me wrap up with that. Whoops, duct tape, you never know when it's going to come in handy. The development of the Ames test as a low-cost, rapid method made feasible the screening of all commercial chemicals to identify what are now called genotoxic effects, the ability to damage DNA. As noted in 1977 in the American Economic Review, even if 6,000 or so new chemicals each year, which is far more than the usual number, were tested using an Ames assay, it would only cost $3 million, quote, a tiny fraction of what researchers at the National Institutes of Health spend chasing apparently non-existing cancer-causing viruses. This is at the heyday of the efforts to try to find cancer viruses to develop human vaccines against cancer, which was a boondoggle. So that was the contrast. So according even to economists, it was not irrational to try to have some basic testing of chemicals in order to inform public policy and regulation about environmental health and safety. But in the US, the passage and administration of Tosca really thwarted that prospect. And this was largely due, as I've tried to show you, over the final language of the bill, which tilted the burden of proof for chemical safety to the government, and also through the interpretation and administration by the EPA over the course of the early 1980s. Now, it's interesting to contrast this with the fate of mutagenicity testing in the sphere of pharmaceuticals. So since 1962, the law for pharmaceuticals has put the burden of proof squarely on industry to show that their products are safe and effective before they can be marketed. So it's kind of the opposite of Tosca, where the government has to show that something is unsafe in order to extract testing information or have some restrictions around that product. And in fact, my suspicion is that it's because of the effectiveness of the 1962 revision to the Food and Drug Act that the commercial chemical industry in the 1970s was so keen not to have comprehensive chemicals research under the same legal framework. So what the FDA does, they don't need to issue rules to get pharmaceutical companies to use mutagenicity testing, because companies are highly incentivized already to use any inexpensive and quick test that's available to them. And the FDA issues guidance, and here's just an example of some recent guidance on what kind of genotoxicity testing should be used and how it should be interpreted. And also, I should mention here also, FDA's led a broader trend in US administrative law towards relying on guidance documents, because as I mentioned, rulemaking is a very costly, slow, and ineffective means of trying to get regulatory change. So it's not as if this testing data is publicly available, almost like most corporate data, pharmaceutical toxicity information is not necessarily publicly available. However, one can go to the physician's desk reference to get a list of the chemicals that are used in most common drugs. And a scientific group actually did their own study of what percentage of those were mutagenic. And what they found was only 7% of them showed to be positive on the Ames test, as compared with an average of 20% for commercial chemicals generally. So this definitely shows selection against mutagenic compounds in the drug industry. So it shows that it's possible to use this test. Now, whether mutations are the be-all and end-all of cancer has itself come under question in the intervening year. So I'm not trying to say the Ames test would have been a solution to all of our problems and no one would have gotten cancer anymore, but it was a useful test. And it's interesting to see the very differential uptake of it in the commercial chemicals industry versus the drug industry. And one interview that I did with a toxicologist in a major consumer products company sensitized me to the fact that whereas most of what I've been looking at is commercial chemical companies like Dow or Union Carbide, which make basically the starting material for chemical products, for consumer products companies where their brand name is so important to them, they do have a stronger incentive to make sure that nobody can do an easy test of their products and find out that they're mutagenic. So toxicity, I think, is higher in consumer products, but when it comes to more generic commercial chemicals, if they're selling a chemical just to a computer manufacturer or something, it's very hard to trace exposure issues back to the original producer. So part of it too has to do with kind of marketing and brand name recognition. So as in the homophonous opera, for Tosca, torture was followed by an unhappy ending. If you've seen the opera, you know it does not end happily. And in the end, even for industry, this was not an entirely satisfactory outcome. The reason is that one of the things that effective law can do is to increase public trust in products and in corporations. And Tosca, in the end, was so broken that even industry became ready to revamp it. Interestingly, one of the last laws changed under the Obama administration was an amendment to Tosca, which did change some of these considerations, but it was then implemented after 2016 in the Trump administration. So there haven't been so many changes yet. It remains to be seen whether under the Biden administration, the EPA will be able to put in place a new implementation of the amended Tosca. But it's also worth highlighting that the pitfalls of testing are not only the legal incentives and disincentives that I've covered, but also the fact that no test is perfect, and especially a simple test that basically reifies a particular hypothesis about cancer. As it turns out, the Ames test may only be 60 to 80% predictive for cancer. And the question is that good enough? Do we need to do animal testing? Some toxicologists say you need animal testing because there's no hypothesis there. You just see whether they get cancer or not. Whereas for many of these tests, it really is a hypothesis reliant test. And also it's worth noting that many natural chemicals and foods, it turns out, are also mutagenic. Our exposure to mutagens is kind of ubiquitous. So then the question is, do we need to worry about industrial pollutants and other kinds of synthetic chemicals being mutagenic? I think we probably do need to think about it. But interestingly, Bruce Ames, who developed this assay himself, took a kind of anti-regulatory bent in the 1980s and 90s. Last but not least, as I've been thinking about this, based on the work of Sheila Jasanoff on regulatory knowledge, it made me wonder if we can also talk about regulatory ignorance, things that we don't know, because of the way in which knowledge is institutionalized in the US chemicals law. Yes. Anyway, that is my story for today. And I just want to thank you all for listening and mention that in between when I decided to speak on this and today, the article on which much of this was based just came out in Science, Technology, and Human Values. So you can certainly still access everything I told you today, not just through the recording. And I also have a co-authored book coming out that also explores issues around environmental chemicals if you're interested in more. Thank you very much. And I'm, of course, happy to take questions from either the in-person or remote audience. Yes, please.
That's another avenue of.
Yes.
I realize that's not what you're.
Yeah, no, and actually, it's not so common within the science and law literature to look at administrative law. That's really where I've been focusing on. But what you're talking about is torts. And I have to say, because the administrative regulation is relatively weak and difficult to change, a lot of the legal activity ends up being precisely on torts, liability issues. I mean, there have been instances in which action is taken. It's easier to do on consumer products or drugs in which the consumer knows their exposure than it is in the kind of things that are just in our everyday products. I mean, the thing about the chemical industry, it's been called industry's industry. The chemical industry basically makes the starting materials for almost every sector of the economy in one respect or another, whether it's agriculture, pharmaceuticals, electronics, you know, so many clothing, textiles, so many aspects of our lives now rely on chemicals that it's very difficult to trace exposure back to the producer of the original material. So I think that, I don't know if chemical companies are protected per se, but if a company makes a monomer that's used to make a polymer that's in your computer casing, and you are exposed to that, whether you can legally and straightforwardly trace back to the original producer of that chemical, I'm not sure. I'm not a lawyer, I should say. I'm a kind of a biochemist turned historian. So if there was a lawyer in the room, or if there is a lawyer in the room, they could provide a better answer. But my sense is that torts has not been as effective in the realm of commercial chemicals. And a lot of the other thing that's been difficult, and I've seen this in the news recently, is that the law is often reacting to incidents of harm. So for instance, if Dow Chemical Company put a lot of really nasty toxic chemicals in the environment before there were stringent laws to prevent that, or early in that process, it becomes very difficult to go back and hold that company liable. And I think many of the contaminations that concern people now are very old. And it's also worth emphasizing that many of our problem chemicals are very old. Many of those high volume chemicals haven't changed in 50 years. And in addition, we often think of synthetic organic, chemicals, but many other kinds of compounds like mercury and lead, which have been produced by humans for hundreds of years, still remain, real dangers in terms of human exposure. So, and that's part of what that residues book is trying to wrestle with, is just the anthropogenic change that chemicals production and their use over human history has resulted in at the moment, and how difficult it is for regulatory systems to be effective in cleaning that up. Oh, yes, go ahead.
What role state regulations have to play in the overall picture of the Professor of California?
Yes, this is a really, really great question. And I have a section on Prop 65 in one of my other chapters. So one of the things that happened in response to the chapter that I've just told you about, this historical chapter, but also this book chapter, is that environmental activists began to look at other jurisdictional levels and other approaches to try to get better control of environmental chemicals. And this both meant an emphasis more and more on right to know initiatives, because in fact, publicly available data was so poor under the legal frameworks, but also states themselves began to issue toxics laws to try to provide more stringent regulation, because Tosca was such a weak tool for chemicals regulation. And the story of the passage of Prop 65 is really interesting. This is California's toxics law, which was passed, I think it's either 1986 or 1987. And it's just after the kind of failure of Tosca to implement better chemicals regulation. It was a brainchild of David Rowe at the Environmental Defense Fund and Carl Pope at the Sierra Club. They wrote the proposition. For those of you who have never lived in California, there's this mechanism by which the citizens themselves can vote on laws, and not through the legislative process, but just by popular ballot can pass laws. And Prop 65 was this California toxics law. Industry probably didn't take the law seriously enough, because it seemed a long shot that it would be passed. And especially because this is when Governor Duke Majan who was a Republican governor, was up for re-election. And he was quite a popular Republican governor. And the kind of unthinkable happened in which he got reelected, but the law also passed. And because of that, the California Prop 65 has become probably the most stringent toxics regulation in the US. And because California is such a large market, it basically affects the whole nation when it comes to consumer products. And you've probably seen Prop 65 warning labels on products yourself and debates about them. It worked through a kind of a right to know. I mean, there was a whole move towards greater labeling, which ironically is kind of part of neoliberalism, which is often associated with anti-regulatory approaches. But the idea is, and now allow consumers to, through having better information, to make better market choices instead of having regulation by a paternalistic government. So Prop 65 is a right to know law, which labels things, but there were also some other provisions of the law, like not dumping into waterways things that were toxic or carcinogenic. And it specifically focused on carcinogenic and mutagenic substances. And it didn't, unlike Tosca, it just said, if something is identified as a carcinogen by the National Toxicology Program or IARC, there may have been one other agency, then it'll be regulated. So it wasn't about whether things should be determined to be carcinogenic, but it took the views of certain international and national organizations over carcinogenicity as the framework. So it was a pretty small group of chemicals that were regulated. It was about 200, but that still affected a lot of products in California. And as David Rowe likes to say, because I had a chance to interview him, companies don't like having their products labeled as having a potential carcinogen. So it's a very effective tool in getting companies to reformulate their products. Industry since then has fought and defeated every other attempt at having a toxics law quite like that in other states. But Prop 65 also hasn't been preempted by the federal government. So like some of the car emissions laws in which California leads the nation, it sets a kind of a national standard. So, and in fact, it has played a role in an international sense, because a lot of concern about international chemicals trade is that for the free trade of chemicals from a kind of, kind of democratic capitalist point of view, you don't want to have what are called non-tariff barriers to trade. Can be a non-tariff barrier to trade if different countries have different toxicity regulations, because it's very difficult for the same product to cross national borders on that basis. So the Organization for Economic Cooperation and Development, the OECD, was really trying to harmonize all the different national regulations. It was spurred in many ways by Tosca. That's what the chapter after this is about. It's called Chemical Passports. But things like Prop 65 really disrupted that, because if you have national regulations that are relatively, lax, and then a state has more stringent regulations, it's very difficult for international organizations to have harmonized regulation. And I think it also points to the fact that for environmental organizations, internationalization is often a drag on their efforts to reform. They often have the most success when trying to deal with different jurisdictional levels and disrupt these very global standards. Anyway, that was a longer answer than you wanted, but it's a really, really great question. And I hope to do a little bit more on that in my book. Are there any questions from the remote audience, or are they quiet? Oh, well. Any other questions? I don't think you expected to see a biosynthetic pathway today. Jim, what are you going to?
I have a sort of technical question about the process that underlies the Ames test. In the diagram you showed wherein the rat liver enzyme was passed through the salmonella and then culture on a culture. And then on the right-hand side of the image, the same thing that added, Ames added a second compound.
Yeah.
So is on the left what we're seeing, this enzyme performing normally, and on the right is it what is the mutagenic technically doing here? Is it generating an excess of the extract, or is it creating a variant?
So what's happening is that rat liver extract is metabolizing that possible mutagen into all kinds of other compounds that might be interacting with DNA. And at least some of those compounds are causing DNA mutations. And a few of those DNA mutations are actually restoring the function of the broken enzyme. So the positive test, the ability of that cell to grow again, is an indication that it's a mutagenic chemical. And I'll show you this test. They actually put everything in a test tube and then spread it on a plate. But I think I left in at the end, I have a slide from one of his papers. Oh, did I take it out? Oh, I took it out. Sorry. I took it out because it was just taking up too much space. And now I've thrown off the thing. But you can also put the chemical on a little disc in the middle of the Petri dish and then let it diffuse out. And often what you see in that case is a halo of cells around the disc. And that's because at a high concentration, the chemical is so toxic, no cells can grow. And then it reaches a point at which it's not so toxic and the cells can actually survive the chemical. But that's when you see the mutagenic effects of that chemical, causing a whole lot, at that high dose, a whole lot of mutant revertants. So, and this is just like a plus minus test, right? It doesn't give you quantitative information about how carcinogenic something is. And that's one of the many complexities about this kind of testing, is that you have to be able to extrapolate from a bacteria to a human. And there's another measurement that you need that's not just whether it causes a mutation, but its potency as a carcinogen in the human body. And there were a lot of debates in the 1980s and 90s about how do you get from mutagenicity to potency. And it's a really complicated problem. But you know, at the same time, the whole validity of the test is also tied to animal testing. And there were also attacks on whether animal testing was as predictive as people thought. And it's kind of like a house of cards. Like you have to have it tied to something, right? Or else the whole thing collapses. And part of what I want to emphasize, I mean, I talk about regulatory ignorance, and there is a lot of, there are many ways in which the information we have is not sufficient, and it could be better. However, there's a literature that's called agnotology literature. Instead of epistemology about knowledge, it's about ignorance, okay? It's philosophy of ignorance. And this is Robert Proctor and London Schiebinger edited a book by this title, and that term has kind of caught on. And there's a tendency in the agnotology literature to be a bit conspiratorial. Like the reason we don't know things is because people don't want us to know them, okay? Whether it's the military making things classified or corporations making them secret or whatever else, people don't want us to know things. And so they prevent this information from being produced or being circulated. And there's definitely a lot of that in the world. But even if we had all the tests in the world, in this sphere and in cancer biology, it's not clear that would lead to perfect regulation. And so one of the things that I want to show in the book is the scientific and technical complexity of the problem, so that there are ways in which corporate interests are distorting what can be known. And at the same time, even if that weren't happening, it would be difficult to get to a really robust policy that would ensure that nobody gets cancer. And in fact, I mean, I don't know whether I agree with this point of view or not, but there are people who basically think of cancer as stochastic. Like you can inherit more or less of a predisposition, but like it's just, you know, exposures and whether they damage a particular gene that happens to be related to a tumor, there is a lot of chance there. So developing cancer can just be 5 unlucky mutations, okay? So it's not necessarily an easily preventable thing. And this is part of why some people see cancer as just a disease of aging, a kind of breakdown of the maintenance of DNA, because our DNA repair enzymes, because we have a whole battery of ways in which cells try to prevent and correct DNA damage, and that breaks down with age. So yeah, that's part of whether controlling mutagenicity as a way to prevent human cancer in the end was complicated in all different kinds of ways. And I hope to capture that complexity. But clearly, as you can see from this talk, industry is not off the hook. So, yes. Question?
Yes.
Okay, and I'll repeat it.
Questions that come from virtual audience.
Okay.
So typically in drug discovery, it is revealed that hoped-for activity is not present when going in vitro to humans. It seems that without a mandate, it's difficult to see why industry would voluntarily generate data that puts its products in a poor light and may not even be relevant to people. Do you have any comments?
Yeah, so did everybody hear the question? I think, should I try to repeat it? So in drug discovery, it's often the case that moving from in vitro to whole animal testing and human testing has disappointments along the way. So the question is, what incentive would a company have to develop or share data that might endanger its product line? And that's exactly the point of the analysis of Tosca, is that one would have to build in a legal incentive for companies to do that in order for it to happen, because the market incentive isn't there.
How does the US testing compare to the European testing? Are we advanced or are they advanced more?
I would say that in general, Europeans have more testing, but the whole system is different in that, and I should say that this is still kind of under development, because in 2007, the REACH law is the registration, authorization, and control of chemicals law that was an EU-wide chemicals law was passed, and it's being implemented over time. And it looked much more precautionary than Tosca. And in fact, there is a general favorable attitude toward precautionary laws. And precautionary laws basically say, show me it's safe before we use it, whereas the US law says, show me it's dangerous before we restrict it. So European law is more precautionary. At the same time, the way in which REACH has been implemented has led to it having less of an impact as its advocates originally hoped on changing things. And many different things are excluded from REACH, low volume chemicals, polymers, there's all kinds of exclusions. And I think the biggest problem on the European side is that, and this is true in the US as well, but we don't get to this point, industry often has an asymmetry of information in their favor. They often have much more information than a government agency ever will. And because the dossiers that are involved in authorizing chemicals under REACH are usually consist of industry data, and it's very difficult to imagine who else would do it because it's expensive to do this kind of testing, they're able to control the process in ways that favor outcomes that they want. But in general, it is a more precautionary environment legally. And the US is a very adversarial environment. And in Europe, over the decades, there's been more of a tendency for regulatory agencies, stakeholders, and experts to work together to come up with frameworks rather than it being kind of hammered out in an adversarial way. A long time ago now, in the 80s, Sheila Jasanoff, Ronald Brickman, and Thomas Ilgen published a book called Controlling Chemicals, which is a really good analysis of how the different legal regimes resulted from different political cultures, US versus Europe. I think they look at Germany, UK, and the US. Yes?
It kind of freaked me out when you said that there is certain foods that are mutagenic also, and so I Googled it while you were answering other questions. And it's very interesting, at first it started out with, grilled beef, and I thought, good, I never do that. And, but then it goes on. There's lots of things that you can even boil beef and it does it. But also, a lot of these same foods, charred beef also has something that is anti-mutagenic. So.
Yep, this is a really great issue, and I have a whole chapter in the book on the debate over mutagenic and carcinogenic compounds in food, natural and synthetic. And Bruce Ames got very involved in this area in the 1980s, testing all kinds of different food compounds and finding that many things in broccoli, mushrooms, as well as kind of that nasty mold on peanut butter called aflatoxin. Like some things are naturally bad. Aflatoxin is probably the most potent natural carcinogen that's been identified. It's actually linked to damaging P53, which is a tumor suppressor gene. So there's a reason why that one is particularly nasty. But anyway, a lot of them are not so potent as that, but still prove to be mutagenic. And at the same time, the complicated compounds in these foods also have antioxidant properties. So Bruce Ames decided by the late 1980s that you should just eat as many natural foods as possible and don't worry about mutagens, that having antioxidants in your diet will protect you. He may or may not be right. And as I said, he kind of became this libertarian in his ideas about regulation. But it's a really complicated area. And of course, in general, the area around cancer and diet has been fraught with controversy, in part because epidemiology is a really complicated tool to use to try to look at heterogeneous populations in which people are exposed to all different things and, ferret out these, correlations. So I do have an article. I've edited another book since the description that Scott Levy used in introducing me, that's called Risk on the Table. That is my chapter on eating mutagens is in there. But in addition, there's a lot of other chapters on changing ideas about risk in food, whether it's antibiotics or arsenicals or salmonella on greens. And the 20th century and industrialization of food has generated a lot of kind of conundrums in which sometimes the things that are developed to try to make food production more efficient and safe can generate their own risks. Like for instance, the kind of, pooling of foods in packaging so that if you have one contaminated spinach leaf, it can get in a whole lot of spinach. I mean, a lot of aspects of mass production actually lead to risky situations. So, and also the fact that antibiotic use means that we actually select for antibiotic resistance, which then gets in other kinds of foods. So this is a great area, and there's lots more that could be said about it. But if you email me, I'm happy to send you my article.
Another question from online. Do you think that the majority of the population would understand products better by having more information on the label, or would they ignore it? To be honest, I wouldn't recognize most chemical names.
This is a great question, and it also gets at whether the informational strategy of regulation is really effective or not. So the FDA in particular turned towards more and more labeling, especially in food regulation, on the presumption that consumers would be smart and intelligent and make their choices based on what they read on a label. And I think what we've seen in the last 30 years is that that's not necessarily the case, even for intelligent consumers. We're in a rush in the grocery store. Who has time to read every package? And certainly if what you have is the ingredient list, even natural substances that are in the food, are going to look weird if they're a chemical name. So it's not clear to me that labeling is always the answer. At the same time, I want to be a little contrarian and say that those people who distrust the kind of command and control regulation of just the government saying this is what we should do and this is what we should do also have a point, because the more like scientific knowledge keeps on changing, and what we thought we knew about risk often keeps changing too. And if you have laws that are very non-specific, then they tend to be subject to political control in terms of how they're interpreted. But if you have laws that are very specific, then they're often overtaken by new knowledge, which renders them obsolete. And this is just a conundrum of regulatory science generally. So I think, again, it's like one can criticize what we have, but it's also important to recognize that sometimes the obvious alternative might not work better. And I don't have a good solution, and I'm a historian, so I don't need to. I only predict the past, and I can get it 100% right. But yeah, this is the question about labeling is a really good question. I think hasn't proven to be as effective a tool although it tends to be extremely popular. You can see it now on cosmetics now, on just about everything. It's easier to require a label than to actually require companies to synthesize things differently or formulate things differently.
Well, thank you very much.
Yes.
You're on the hot seat for quite a while. If we keep you there any longer, I'm afraid you'll become carcinogenic.
I'm like,
Okay, thank you very much. It's a wonderful talk. Thank you all for joining us.